Hello. Today I want to talk about one of the fundamental algorithms of number theory, also of abstract algebra in general, the Euclidean algorithm, and its big cousin, the extended Euclidean algorithm. These are algorithms where I'm not going to actually state the algorithms in general. At first, I'm just going to state what they produce. So the Euclidean algorithm, you start with two numbers, a and b, natural numbers, whole numbers, right? And then it's going to return their greatest common divisor. So here, really, you do want non-zero natural numbers, right? You want positive natural numbers, just so they have a well-defined greatest common divisor, right? Now, the extended Euclidean algorithm is also going to start with non-zero natural numbers a and b. And then what it does is it actually finds integers x and y such that some integer times a plus some integer times b equals their greatest common divisor. So it's actually going to express the greatest common divisor of a and b as some multiple of a plus some multiple of b, some integer multiple of each, right? So this is what is accomplished by the Euclidean algorithm and what is accomplished by the extended Euclidean algorithm. I haven't said the steps and how you carry out the algorithm yet, but that's because I think, as you'll see in a second, these are algorithms best described in example. Of course, you maybe need to describe them more precisely if you're trying to code them, right? If you're trying to implement them in a programming language. But here is, I think, as far as a human understanding of them, this is the best way to see it, is to just see it in an example. So let's start with an example where we use I'm going to use the Euclidean algorithm to calculate the greatest common divisor of two numbers. And in particular, I'm going to calculate the GCD of the numbers. I'm going to do 12 and 45. Right, so I'm going to use these two as my numbers. So here's what you do for the Euclidean algorithm. So what you do is you're going to take your two numbers and you're going to perform long division on those numbers. So you're going to say, okay, 45 and 12. If I do long division with those numbers, it's going to go in 3 times, right? And then I subtract off 12 times 3, and I'm left with a remainder of 9, right? Except instead of formatting your long division in that sort of vertical way that it's often formatted in when you first learn arithmetic, instead format it as an equation. Format it this way. Say 45 is 3 12s with 9 left over. Format it horizontal. It's still just long division, but we're formatting it side to side instead of up and down. So that's how I want to write the first step of my Euclidean algorithm. Now, repeat this. Do long division over and over again, except on your next step, have your numbers take one step to the left. And what do I mean by one step to the left? Your old divisor of 12 becomes the new dividend. Your old remainder of 9 becomes the new divisor. And now do the division again. So what is 12? 12 is 1 9 with 3 left over. And now repeat, right? Do this again. So make the old divisor become the new dividend, and the old remainder becomes the new divisor, right? Now do long division with 9 and 3. So this is going to go in 3 times with 0 left over. As soon as you get 0, this is when the algorithm terminates, right? So that the fact that we got 0 as a remainder, this means that we stop. And when you stop, whatever was just above the remainder, just above the 0, that's your greatest common divisor. So the algorithm is done. And this number right there, this is the greatest common divisor, right? So the GCD in this case would be 3, right? So that's what this algorithm returned. GCD of 45 and 9, right? And the, sorry, 12 was the other number, right? So the GCD of 45 and 12 is 3 by the Euclidean algorithm. Right? So that's the Euclidean algorithm. What you do is you start with your two numbers, you do long division, then do long division again using the old divisor as the new dividend and using the old remainder as the new divisor, and then repeat that process until you get 0. Right, so that's how you can, and then the second to last. So 0 is always going to be your last remainder. The second to last remainder, that's your GCD. So that's how you run the Euclidean algorithm. Like I said, you could describe that in symbols, but I think it's something best seen just in an example. Right? So there's our greatest common divisor of 45 and 12. Also, you can see that this is correct just by, these numbers are small enough you could just do it by brute force listing and you can see that it's correct. What are the divisors of 12? 1, 2, 3, 4, 6, and 12, right? But 4, 6, and 12 don't divide 45, right? None of those divide 45. So 3 is in fact the greatest divisor that's common to both 12 and 45. So it worked, right? It gave us what we should have got. Now, I also want to do, this is part 2. I want to do the extended Euclidean algorithm. So what is the extended Euclidean algorithm? So this is going to be, right, the second phase is I want to show how you could use the extended Euclidean algorithm. Right, to find what it gives you, right? To find integers x and y such that 45x plus 12y equals 3, equals their greatest common divisor. Right, this is what the extended Euclidean algorithm accomplishes. And how does it accomplish it? Well, here's what we do. Phase 1 is to run the Euclidean algorithm. This is why it's called the extended Euclidean algorithm, right? The first part of the extended Euclidean algorithm is the Euclidean algorithm. So I'm just going to copy the equations from the Euclidean algorithm. That's the first thing I want. So I'm going to take these equations and I'm just going to write them down. So I have, what were these equations? They were 45 equals 3 times 12 plus 9, right, was one equation. I had 12 equals 1 times 9 plus 3. And I had 9 was 3 times 3 plus 0. These were the equations from the Euclidean algorithm. And it turns out here, we're actually not going to need the last one. So you can actually ditch the one that had the 0 in it. What we really need are the two equations that had we really need the equation that ended with the greatest common divisor. That's the one that we really want to start from. And then here's what we're going to do is we're going to take these equations. So this is phase 1, is just copy down those equations. Phase 2 is I'm going to solve these equations for the remainders. So I'm going to slightly rewrite these equations. And I'm going to rewrite them like this. What do I mean by solve for the remainders? I mean, write 3 equals 12 minus 1 times 9. Right? I took that same equation, 12 equals 1 times 9 plus 3, and I solved it for the 3. I subtracted over the 1 times 9. Right? And then what I'm going to do, I'm not only going to solve for those remainders, one at a time. As I solve for the remainders, I'm also going to substitute. So solve the remainders and substitute. So what do I mean by that? Well, this next equation tells me I could solve it for a 9, right? So solve it for 9 and substitute that for 9 in this equation. So what is 9? Well, the Euclidean algorithm tells me that in this context, the way I want to think of 9 is as 45 minus 3 times 12, right? That's what I get if I solve for 9 in the Euclidean algorithm equation. Now, unpack all this. What do I get? I have 12 minus 1 times 45, right, plus 3 times 12. And now I can combine like terms, right? I have 4 times 12 minus 1 times 45. once I combine like terms. That's equal to 3, right? And now I'm done. Think of what we were looking for. We were looking for integers to multiply 12 and 45 by to end up with their greatest common divisor. That's what we just accomplished, right? So we just got that x is, what did I have as what? X was who goes with 45. There we go. And y is who goes with 12. So x is -1 and y is 4, right? There you have those numbers, the 4 and the -1, right? Because we just figured out that 45 times -1 plus 12 times 4 equals 3. Right? And if you check the arithmetic, sure, 45 times -1, -45, 12 times 4, 40, positive 48. Therefore, if you add them up, you get 3. Right? So that is our extended Euclidean algorithm, right? So the Euclidean algorithm is just repeatedly doing long division, right, over and over again, starting with your original numbers and then passing off the remainder and the divisor each time as the starting numbers on the next step, right? The extended Euclidean algorithm takes those equations that you got from the Euclidean algorithm and solves them for the remainders, and then uses substitution to express the greatest common divisor, right, which was that last remainder. Express that in terms of the original two numbers by back substituting through the equations that you got. So, and that's it. That is the extended Euclidean algorithm, right? So that's how you can find those numbers such that ax plus by equals their greatest common divisor. One thing I want to comment on is you can also then, without too much effort, find the solutions to related equations. For example, suppose I said find an integer solution. Find an integer solution to this equation, to 45x plus 12 times y equals 9, right? Well, what would you do? You would use, we actually almost have the solution. Just take what we have above and multiply both sides by 3. Use x equals -3 and y equals 12, right? Just triple the equation that we already have written above, right? So you can solve integer equations like this, even if it's not necessarily exactly the GCD on the right-hand side. Here I had a multiple of the GCD, right? You can also look at related equations in terms of this idea of the GCD, right? Say I said this, find an integer solution to 45x plus 12y equals 1, right? Well, you can say it does not exist. How come? Because the left-hand side, what was the greatest common divisor of 45 and 12? It was 3. So the left-hand side is always divisible by 3. Right? But the right-hand side is not. So no matter what integers x and y you plug into that left-hand side, you're going to get a multiple of 3 because that's their greatest common divisor. On the right-hand side, it's 1. It's not a multiple of 3, right? So there you have, this is sort of the, this is the equation that the extended Euclidean algorithm directly solves. But a lot of related equations, if you're looking for integer solutions, you can kind of think of it in terms of the Euclidean algorithm and extended Euclidean algorithm. Great. There we go. There's one of the fundamental algorithms of number theory. Thanks.